Does anybody have one? So let's see, we were talking about, actually, let me just say something before I start the real lecture about photons and spin, why massless particles have velocity only in and opposite the direction of motion. Well, the point is that surely these elementary particles, we treat them as though they were points because we don't know any better and because we can get away with it. But they're certainly extended in space in some way. And they might be strings, they might be something else. Anyway, if you have something moving at the speed of light, then you can't have it rolling the way it would if it were the wheels of the thing moving at the speed of light, because then you would have the upper part going faster than the speed of light, and it would just be kind of nuts. On the other hand, if you make a Lorentz transformation, say in the x direction, then distances that are perpendicular to x, like say y and z, don't change, and velocities, am I right about this? Velocities in the x and y direction don't change. Momenta in the x and y direction don't change. And, I'm sorry, y and z direction don't change if you're making a boost in the x direction. So what you can have then is you can have something doing this, because that's r cross p, and so that's circular polarization, effectively, is what we call it. But it's that the angular momentum is pointing in the direction of motion, or you can have it do that, and the angular momentum is pointing in the opposite direction, but you can't have it this way, because then you'd have the thing going, in some sense, faster than c. And that's how I look at it. I've never moved at the speed of light, so I don't really know. Yeah.
But what about in water? Because in
What
water,
about what?
in water, the particle can move faster than the light, the speed of light in water, right?
Well, it just moves faster than the speed of light in water.
Yeah.
It doesn't move faster than the speed of light. In other words, the photon's moving at c, but because of the index of refraction, the speed of light is less.
Yeah. So you can catch up with the light, right?
I haven't thought about this in a while, so let me not go into too much detail. This is a process actually known as Cherenkov radiation. But anyway, so I just thought I would mention that, why it is then that particles of spin 1/2, 3/2, spin 1, spin 2, and whatever, they're massless, they can only have positive and negative velocity rather than all these other ones. Now, let me just remind you that for a photon, a Lorentz for an electromagnetic field or a massless field of spin 1, under a Lorentz transformation, and these, by the way, are unitary operators. You can think of them as matrices if you want, but then they're infinite dimensional. So you see the Lorentz group is non-compact, and its unitary representations are then infinite dimensional, not finite dimensional. Let me switch to my reading glasses. Okay, this is, whoops, that's a lambda inverse, mu, a nu of lambda x. Okay, so in other words, a massless spin 1 field undergoes a gauge transformation when you make a Lorentz transformation. For a massive field, you just get the first term, and you wouldn't need that second term. This is somewhat puzzling, this effect. And in fact, we're dealing with graviton, we have more derivatives, second derivatives. This is related to what happens to a polarization vector under a Lorentz transformation. It becomes either plus or minus I theta, some epsilon mu of k plus or minus helicity, and then it gets this thing, either plus or minus I theta, and then some complex number, alpha plus or minus I beta. You can see I'm taking this from Weinberg because there's more detail than you really want. This is square root of 2 omega k. I'm a little puzzled about that omega k. I hadn't noticed when I copied it down, but a k mu. So this thing is associated, momentum is associated with a derivative, and that's this derivative here. So let me touch on the Ward identity we were talking about somewhat tangentially last time. Once again, I'm taking this, I'm giving you sort of a simplified view of Weinberg. The interaction Lagrangian is something like E A mu J mu. And so if we look at the simplest possible term, we would have something like P prime, lowest order, we'd have something like E A mu J mu, and then we'd have pk, k being the momentum of the photon. And this thing, of course, would be integrated d fourth x. This is just the interaction Lagrangian, and I've, well, let me put in the I because it's IL interaction that comes down. This is just sort of first order perturbation theory, and I'm thinking of an unphysical process. P goes to P prime plus photon because you need two P's in order for this to make any sense. But then we have a very complicated structure here, and I don't want to get us embroiled in all that. Well, this thing will annihilate the photon. Electromagnetic field will annihilate that, and so we'll have something like this: P prime epsilon mu of k, and then J mu of x, say, P e to the I kx d fourth x. So I'm being very sketchy. I'm setting h bar c 2 pi and I equal to 1. I remember hearing that in a talk. Oh, I left, yeah, this. And we can say, well, this thing is epsilon mu of k, some m mu of k. And now I want to point out that k mu, m mu is going to vanish. And so let me show you why that's true. So we have k mu, m mu of k. Well, this is an integral p prime j mu of x p e to the I kx, and we have a k mu there and a d fourth x. Okay. Well, this k mu we can imagine comes from differentiating the phase factor. And so this is in fact minus I integral p prime j mu of x p d mu e to the I kx d fourth x. And now we integrate by parts, and we get I equal p prime d mu j mu of x p e to the I kx d fourth x. You see, by the way, one reason why I wanted to make it this very, very simple example is that otherwise I'd have to have a time-ordered product here, and I'd have to move the derivatives through the time-ordered product. We get these Schwinger terms and so forth. So I didn't want everything to be quite complicated. Okay, but this is a conserved current. Okay, we have. I'm talking about a theory that's gauge invariant, And consequently, we have d mu j mu 0, and so this is equal to 0. So this is an example of a Ward identity. So you have global invariance under phase transformations. That gives you a conserved current. But and so from the point, if you just have the conservation of current, then you can go through this and get k mu, m mu equal to 0. But the other part of the Ward identity, in other words, the part that Schwartz stressed was that if you want this to be Lorentz invariant, then you want that this should go to something like epsilon prime mu of k prime plus some complex number k prime mu, and that should be m mu of k prime. Well, this obtains when you have a massless spin 1 field coupled to some current. And you see, if this thing is to be Lorentz invariant, you want this to be epsilon prime mu k prime, well, m prime mu k prime. Well, then you need k prime mu m mu of k prime to vanish, which is another way of getting at the same Ward identity. So these things are all sort of tied together. You might say, well, there's something mysterious about massless fields, there's something mysterious about gauge invariance. I agree with you. That makes the subject interesting. It's never a dull moment in quantum field theory. That's what's, I think, interesting. All right, the photon propagator. Well, this, of course, is the vacuum of the free theory, time-ordered product, a mu of x, a nu of y. I'm sort of giving up and using the Greek indices because Schwartz uses them all the time, and I forget to Latinize. Anyway, we expect this will be an I integral d4 p 2 pi to the 4th, and then e to the I p x minus y, and then something Schwartz calls pi mu nu of p. And so we want to figure out what that might be. Well, there's a lot of choices, of course. If we start out with the classical Lagrangian, in other words, e squared minus b squared, and then a mu j mu. The equations of motion are d mu f mu nu equals j nu, at least in units with minus 1 equal to 1. And what does this look like? Well, it's d mu a nu minus d mu b nu a mu equals j nu. And if we write, can't resist using this part of the board, a nu of x as an integral d4 p over 2 pi to the 4th e to the I px a tilde nu of p, then and then we apply this and do the same thing for j. What we'll get is essentially minus p squared a tilde nu, something wrong with this piece of chalk, plus p nu p mu a tilde mu is j nu, j tilde nu. And equivalently, we've got here a matrix expression, which is minus p squared delta nu mu plus p nu p mu a tilde mu equals j tilde nu. Something decidedly wrong with that piece of drawing. Okay, well, as Schwartz points out, yes, sorry.
No, thank you. So why can't we just take the Feynman propagator and send the mass to 0?
Which Feynman propagator? The Feynman propagator of the massive field?
Yeah.
Oh, if I recall, that thing has a 1 over m squared in it.
Right. P squared minus m squared plus I epsilon.
Yeah. Let me find it because I don't have this memorized. Where the hell? Does anybody remember where it is? Seems to me there was that Cousins wrote it down. In other words, I think that the propagator from a massive vector field has something like a to mu nu plus p mu p nu over m squared, all that divided by p squared minus m squared. I think it's something like that. And this term goes crazy when you take the limit n going to 0. But again, I don't have memorized the massive. Actually, I know where to find it in Weinberg. I think I know where to find it in Weinberg. Yeah, here we go. Yeah, I mean, it's basically that, so you can't take that limit. On the other hand, if you're not talking about spin 1 or spin 2, but instead of talking about, say, spin 1/2, and I think even spin 3/2, then you can take the mass equals 0 limit of the ordinary massive propagator. So it's just the gauge fields that are complicated. Well, the natural thing would be to invert this. This procedure, by the way, is Schwartz loves to do the thing classically, invert the equations of motion. And the trouble is you can't do that here because this matrix here has a 0 eigen vector, and you can see that if you just take, much better piece of chalk, minus p squared delta nu mu plus p nu p mu on the vector p mu. Well, this delta turns that into minus p squared p up a nu, and this one with that one is p squared, so this is plus p nu p squared, and that's 0. So this matrix has a 0 eigenvector, and consequently you can't invert it. So what people do is they break the gauge invariance explicitly by changing the Lagrangian and quantizing a particular gauge, and then calculate the propagator in that gauge. Another approach, an approach that is simpler and makes a little more sense physically, I think, is to quantize in the Coulomb gauge, which makes everything much clearer, because the del dot A condition, del dot A equals 0, tells you that if you start out with 4 polarization vectors, one goes immediately because of the del dot A equals 0 condition. And then you look at your equations of motion, one of them is a constraint for A0. So that means you can solve for A0 in terms of A vector and the charge density in the theory. And so another component, another polarization vector goes. You're only left with 2. Those are the 2 transverse ones. A0 is no longer in the picture, it's just an integral over the charges and the three vector part of A. And you can then construct a path integral, and then when you construct that path integral for QED, you then have two options. You can either integrate over all gauges by a trick, or, in fact, the nice thing to do is first integrate over all gauges, but only you have ratios of path integrals, so the extra gauges that you're integrating over cancel. And then once you're in that general situation, if you want to go into any particular gauge, you can then do another trick and go down to any particular gauge, such as the gauges such as Coulomb, Lorentz, or the gauges that I'm going to be talking about in a moment. In fact, these gauges are the following: minus a quarter F mu nu, F mu nu. By the way, I describe all this in my book, the chapter on path. So, look it up there. Anyway, the next one is a Lagrange multiplier, 1 over 2c d mu mu squared minus j mu a mu. Okay, so you've changed Lagrangian by adding this term. Now, what does this term do? Well, if you imagine that c is some small positive number, you see that it's going to force d mu a mu to 0. Equivalently, if you consider c to be a Lagrange multiplier, it just tells you d mu a mu is 0. Now, if we take this expression here and the analogous equations of motion, instead of just this, we get something a little more complicated that involves c. Then, instead of this matrix, which is singular, we get this matrix, minus p squared delta nu mu, plus 1 minus 1 over c, p nu p, lower mu, a tilde mu equals j tilde nu. So this is a new equation, no pun intended. Anyway, this we can invert, and the inverted quantity is what we call capital pi mu nu of p, and it's equal to minus eta mu nu minus 1 minus c p mu p nu over p squared, and then this whole thing is divided by p squared. And of course, we're going to stick in an I epsilon in a moment. Just to show you that that is the inverse of that, why don't we just work out the calculation? We've got then I'm going to take this minus sign and flip the sign of this. So I'm going to flip the sign of this with the overall minus sign. So then I'm going to have plus p squared eta mu nu minus 1 over c p mu p nu, and then times this, which is eta mu nu minus 1 minus c, and it's eta mu nu over p squared minus 1 minus c p nu p lambda over p to the 4th. All right, so we want to multiply that out and see that everything works. And you turn it here if you want to get feet up. All right, so what do we get? Well, the first one gives us, oh, hold on, this is, I've got to have this thing consistent. This is mu lambda. nu lambda. Okay. So now eta nu lambda just gives us delta lambda mu, and the p squared cancels. So that's the piece we want to keep. And then we want to hope that anything else cancels. Well, all right, let's just work this out term by term. The first term is this one times that, and that is minus 1 over c. And now we have what? Well, this eta raises the index there, so we have p mu, p lambda over p squared. The next one, so we've done everything with this one. Now we have this guy times that, and that gives us minus 1 minus c. One of the p squareds cancels, so we have p nu, p lambda. Oh, this is lowered to a mu by eta mu nu. And then we have 1 over p squared. And then finally we have the product of these two. Well, p nu gives us a p squared. That turns that into p squared instead of p to the fourth. And we have p lambda, p mu. And then this is plus 1 minus 1 over c, 1 minus c, p mu, p lambda over p squared. Okay, so altogether, this is delta lambda mu. And let me just follow my notes so I don't have to invoke supernatural units with minus one. All right, so this is minus p lambda p mu over p squared, and what's left is 1 minus c, 1 minus 1 over c, minus 1 minus 1 over c, minus 1 minus c. And you see here then everything cancels. This is delta nu mu minus p lambda p over mu p squared. And what do we have here? We have a 1, we have minus c, we have minus 1 over c, and then we have plus 1. And then here we have minus 1 plus 1 over c, minus 1 plus c. And so we have 1, 1, minus 1, minus 1. You have minus c plus c, minus 1 over c. So the whole thing is 0. So this is just delta mu. So this is in fact the inverse, and so the propagator then, why don't we go over here? The propagator then is, we've got an I, p mu nu here. This thing is integral d4 p over 2 pi to the 4 e to the I p x minus y. And now I times that is minus I over p squared plus I epsilon, the I epsilon giving you the time ordered product. And then we have eta mu nu minus 1 minus c, p mu, p nu, and now it's over p squared. And you might say, oh gosh, but p squared could be 0. Well, it could be 0, but you're integrating d4 p, so the p squared equals 0 is a set of measures 0 there. Anyway, you have the I epsilon regularizing that singularity. As Schwartz points out, the minus I eta mu nu in Schwartz's metric is minus I. And so this thing, for the space components, the 3 space components, it's really I over p squared plus I epsilon, which is the same as the scalar propagator. So that's how you can remember what the sign is. All right. Any questions? Now, there are various gauges. And the gauge that is used most often in perturbation theory is called the Feynman gauge. And by the way, the apostrophes in front of T. I think it means head. Anyway, this gauge is C equal to 1. This chalk makes lovely marks, but it just does not stand up. All right, pi mu nu, if you set C equal to 1, then this is just minus I, eta mu nu over p squared plus I epsilon. Well, that is, you know, the simplest thing I mean, how could you, what could be nicer than that? It's just the scalar propagator in the massless scalar propagator in the three spatial directions, and then a screwball propagator in the time direction. There are other gauges. There's the Lorentz gauge, and this is C equals 0, and here we have I pi mu nu is minus I eta mu nu minus p nu over p squared, all divided by p squared plus I epsilon. So obviously this is a more complicated gauge. And then if you look at the original, let's turn around this way. If you look at the original Lagrangian with the gauge fixing term, which is sort of Lagrange multiplier term, if you send C to infinity, what happens? You get back the classical Lagrangian. So that's the gauge without any gauge fixing. And without any gauge fixing, that for some reason is called a unitary gauge. But it's what you get in path integrals if you just integrate over all the gauges. In fact, as far as I know, you can take any theory, just write down the classical action, integrate over all the gauges, and that's the correct, if you have ratios of path integrals, that's the correct expression. So unitary is C goes to infinity. Then there's a light cone gauge. And that is n mu a mu equal to 0. And here n is a light-like vector. There's the Coulomb gauge, which I like very much, and it's the gauge, it's one of the gauges, it's the gauge perhaps that Schwinger was fond of, and Weinberg also makes use of it in his volume 1. So you have Zelda A equals 0. And then there's the Fock-Schwinger gauge, which I had never heard of until reading this chapter of Schwartz. It's x mu a mu of x equal to 0, which is quite a strange gauge. In any event, in the general gauge, which is called an arc-C gauge, what we have is I pi mu nu of p, and as I said, it's minus I over p squared plus I epsilon, so that's the normal part, and then eta mu nu minus 1 minus C p mu over p squared. Okay. Now, if we look at this, we can see that we don't, if we have some amplitude, so some amplitude m, and it's going to be pi mu nu times some, I don't know, let us say z mu nu, or whatever the rest of the amplitude is when you've done a certain amount of perturbation theory. You might have a term like that. Okay. That means, you see, that this will have ... and then there'll be a 1 minus c over p to the 4, p mu, p nu, expect that your calculations will not involve the gauge fixing. Just don't turn the, I'm just looking for chalk. You expect that your amplitude, you don't want your amplitude to depend. I mean, this is a number. This is, you know, square, you activate squared gives you a cross section. That shouldn't depend upon what gauge you choose. So in other words, what you've got is P mu, P nu, Z mu nu had better be 0. So that's a check on your calculations. And I must say, when I was a graduate student and heard such a thing, I said to myself, oh my God, I do not want to do calculations where we have to check these things this way. You used to imagine how complicated it would be. Anyway, it's a little bit like word trading. Okay, well, now we're going to, first, are there any questions? By the way, I'm skipping over some parts of chapter 8. I think you can just read them because they're highly verbal and somewhat suggestive. And I had the feeling that there was a breeze blowing in my face because Schwartz was waving his arms so much. Anyway, I think it's good for you to read it, but you know, you can't do everything. All right, the next topic is Scalar QED, and this is in chapter 9. And the fact is, there is a scalar charged field. It's the Higgs before symmetry breaking. And although it's 2 charged fields, actually 1 charged field and 1 neutral field. The neutral field is complex. It has a non-electric charge, actually. Okay, what is the action density? It's, oh, it's really great. It's a lovely mark for the breaks. Okay, d mu phi star. Star, Schwartz does a nice thing here, and something I've done in the past also is use star to mean Hermitian conjugation or complex conjugation, depending on whatever your thing is. If you have a matrix, you might want to use a dagger.
Should use a dagger. Should use a dagger.
It depends. I don't know. The trouble is, when you do certain things, you want a star.
I think we ought to.
Especially if you're talking about, well, this is neither here nor there. d mu p minus m squared p squared. All right. Now, what is d mu? Well, that's just the covariant derivative that we've been talking about. It's the ordinary derivative, and then plus i.e. a mu phi. And of course, this thing, d mu phi star is of course d mu phi star minus i.e. A mu is a real field. Phi star. So these are the terms. Now, this Lagrangian or action density clearly has invariance under a global transformation, phi prime of x, e to the minus I alpha, phi of x, or plus I don't know why, minus I. On the other hand, because of the way in which we've used this gauge field, it actually even has invariance, it has gauge invariance, namely e to the I alpha of x, phi of x. So you have a space-time dependent phase transformation, so you have gauge invariance there. So this is the electromagnetic field and some charged field. Okay, so we have current conservation. Now, if you do the equations of motion, I was just going to write down the equation of motion, but I'm moving through this lecture so fast I have time to do it. Do you want to see me derive the equation of motion for the field phi from this? All right, there's a nod, yes. All right, let me get a piece of chalk that'll last for maybe one or two equations. Okay, well, this is d mu partial of this with respect to phi comma mu is equal to partial L partial phi. So those are Lagrange's equations for the field phi. Phi comma mu means the derivative of phi with respect to x upper mu. All right, well, let's look at it here. I don't know why I'm holding this because I skipped this in my notes. The derivative with respect to, all right, let me lower this one and I'll raise that one. Then this would be d mu of d mu phi star, okay, is equal to partial L partial phi, and what would that be? Well, there are several terms. There's a phi in here, and that phi in there looks like this. So it's I-E A mu, and it's multiplied by d mu phi star, and it's I-E A mu, right? Right. Okay, that's that one. And then that's it, apart from this one, and that's minus m phi star. And this one is d mu plus, there's a complex conjugate, so it's minus I-E A mu phi star. And so what is it? This is box. There's an m squared there. And so we have box plus m squared phi star on the left equals, and what does it equal? Well, it's this term, which would be I-E d mu of a mu phi star, and then from here we get plus I-E d mu phi star a mu. And I should decode this because this is I-E, let me just, yeah, all right, I'm going to leave it this way. I-E d mu, wait a minute, these indices are not right. You shouldn't have both of them down. Where did this come from here? Yes. This is an upper index on the mu. So it looks like that. And then this one is plus I-E d mu phi star a mu. So that's the first term. The second term is a minus, so that's going to be plus E squared phi star phi. No, there isn't any phi. Phi star, and also the indices are screwed up here. Partial with respect to phi. Yeah, this is an upper A. And so this looks like this. And so that's what it looks like. Let's see if that's what Schwartz has. Actually, Schwartz has the stars in a different. No, wait a minute, that's right. Yeah, there's a, I copied down Schwartz incorrectly, there's a pi star there, or maybe there's a typo in Schwartz. Where, does anybody have Schwartz here? Yeah, we're back here. Yeah, I copied it down wrong. Okay, so this is correct. If I had done the opposite equation, namely d mu partial L partial phi star comma mu equals partial L partial phi star, then I would have gotten the equation box plus m squared phi is minus I-E a mu d mu phi minus I-E d mu of a mu phi plus minus e squared a mu phi. And what you see is if you go from the phi to the phi star or the phi star to the phi equation, the sign of e changes. So you have I-E goes to minus I-E, I-E goes to minus I-E, and E goes to minus E, but it doesn't make any difference there. Okay. And there's an equation, if you compute the current, then the rest of this is d mu f mu nu equals j nu, where j nu is whatever it's supposed to be. All right, now, for some reason, Schwartz skips no, I'm going to go back there, I think I've got room. Schwartz skips the next step, which I think is very important. And so let me emphasize that. Imagine we've got two fields of the same mass. And if we're talking about the standard model, then we'd be thinking of, say, the fields before symmetry breaking, so everything would be massless, so all the fields would have the same mass. So we can write this as integral dqp, 2 pi cubed, 1 over square root of 2 omega p, and given mass there. Then we have a1 of p e to the minus I px plus a1 dagger having of p e to the I px, like that. And then the same thing here for phi 2. Notice, same omega p. All right. Now, obviously, physicists don't want to have to do this all the time. It gets tedious. Okay. So you don't want to have to write down 2 copies of something that's almost the same because the mass is the same, the phase factors are exactly the same. The only thing that differs from this line to that line is you replace 1 with 2. So we have 2. These are 2 neutral scalar quantum fields. Okay, here's the trick. We say phi 1 over root 2. Well, let me use a curly bracket. Phi 1 of x plus I phi 2 of x. Okay. Now when we combine things, here's what we get. We get just one integral dqp, 2 pi cubed. We get 1 over square root of 2 omega p, that's fine. Same phase factor, e to the minus I px. Now we have 1 over root 2, a1 of p plus I a2 of p. And then we have plus e to the I px, 1 over root 2, a1 dagger of p plus I a2 dagger of p. Okay. Now, look at this carefully. You see, up here, this is the dagger of that. But now, this is not the dagger of that. See, because if you daggered this, you'd have a minus I here. We have a plus I. So, we rebaptize this as A of P, and we rebaptize this as B dagger of P. Weinberg often calls it instead A conjugate of P dagger. So it's the creation operator for the antiparticle. Most books don't want to have the sub C, and so they just switch the letter to B. But then they've got 2 letters. I think Weinberg's technique choice is better. All right, so this is really important, and it's not emphasized in most books. And the fact that there is this root 2 is why, when we write down the action for a charged field, we don't have 1 over 2 here, because the 1 over 2 is already represented in the 2 1 over root 2s. All right. And I've been talking here about scalar fields, but the same business applies to vector fields, whether massless or massive, and so forth. Spinor fields. Okay. And of course, what we don't know yet is what's going on with the neutrino. The neutrino is neutral, so the sort of things that have to happen for charged fields don't have to happen for neutrinos, so we don't know what's going on with neutrinos. I wish somebody would figure out how to use a neutrino detector to detect nuclear weapons being moved around or hidden, and then we get this thing cleared up in a few years without any trouble. Any questions? Nobody wants some sweets? Okay. All right, now let's get back to perturbation theory and the interaction Lagrangian. And now in this interaction Lagrangian we have cubic terms and a quartic term. Yeah, maybe we should just mention what those are. You see, if we look over here and multiply this out, we have minus I e a mu phi star times d mu phi, that's a cubic term. And then we have basically the complex conjugate of that. Then we have a term that's a mu squared phi star phi with an e squared. That's a quartic term. So I'm going to look at, I'm going to think about the, the cubic terms first. And as you know, when you are doing perturbation theory, what you have is the e to the I, you have the time-ordered time-ordered, I don't even know, I think it's easier to write this down. The language of mathematics is easier than the language of English here. You have the time-ordered e to the I integral interaction Lagrangian t forth x. You've got that. And then you've got some initial state, and you've got some final state. And so this is sort of what you're dealing with for perturbation period. And, okay. So, this, by the way, is quite simple. I mean, you just have some creation operators here, some annihilation operators there. These are just, this is just something cubic and quartic in the fields. And if you expand one order, well, the first term is just 1, and that is 0. That if the final initial states differ as they normally do, that term vanishes. Then you have simply an integral I d forth x, and then higher terms. And so that's where things come from. Now, the propagator for the complex field, phi of x, phi of y, this thing turns out to be integral d forth p. Boy, this is short. 2 pi to the 4th I over p squared minus m squared plus I epsilon e to the I p x minus 1. Okay, so that's our propagator for the charged field. And Schwartz sometimes writes this in terms of dotted lines. It's hard to write dotted lines. I'm going to just write solid lines. There. On the other hand, the photon propagator looks like this. Easy to write, curvy line, and this is time-ordered a mu of x, a mu of y, 0, and it's going to be d forth p, 2 pi to the 4, minus I, p squared minus I epsilon. Hold it down. How come I have minus I epsilon and plus I epsilon in 2 different places? No, it should be plus I epsilon. Eta mu nu minus 1 minus c p mu p nu over p squared. Okay. So these are the 2 propagators, and in Feynman diagrams, this will be a line, an internal line, and this internal line will be that. The fields I've already written down for you in a sense, but I think it'd be useful to write them again. It's phi of x is going to be dqp 2 pi cubed 1 over the square root of 2 omega p, and it's going to be AP e to the minus I px plus BP dagger e to the I px, and phi star is integral dqp 2 pi cubed 1 over the square root of 2 omega p. So the adjoint of that would have AP dagger e to the IPX, and then the adjoint of that is BP e to the minus IPX. So it looks like that. So let me just to emphasize, this guy here is 1 over root 2 A1 plus I A2. This guy is 1 over root 2 A1 dagger plus I A2 dagger. This one is 1 over root 2 A1 plus A1 minus I A2, and this one is the adjoint of that, which is 1 over root 2 A1 dagger minus I A2 dagger. So these are the annihilation and creation operators. And notice when I wrote them, my left arm was down, so you should, make sure that this corresponds to the definitions on the backboard. All right, now let's see what happens when we have things going in and out and so forth. What does phi do? Well, phi annihilates a particle or creates the antiparticle. I find it easier to use Weinberg's convention where time goes up, because if you just say time goes to the left or right, I mean, how do you keep track of that? Why should time go left or right? Whereas time has a direction, a preferred direction, and up is a natural preferred direction. I mean, if you said time was going down, that would really be silly, right? So what does phi do? Phi creates a particle, an antiparticle, or it annihilates the particle. So in other words, and the way we've written these things, the particle that is stopped here is the electron, or the scalar electron. And the one that's made is the scalar positron. So it makes a scalar positron or stops a scalar electron. On the other hand, phi star, well, it stops a positron. Or it makes an electron, which is this term, and we call that an A here. So we could say here, this is A, this is B dagger, and this is A dagger, and this is B. So that's the picture. And now, if we look at these trilinear interactions, the trilinear part of the interaction is minus IE A mu, and it's phi star d mu phi minus d mu phi star phi. Or if you want, d mu phi star. On the other hand, what we have is not L3, but IL, I times the interaction Lagrangian. Okay. And so I, L3I, is going to be simply EA mu times these things, phi star d mu phi minus d mu phi star phi. So that's the thing that we're going to see. And now we can consider 4 possible special cases here. By the way, the conservation charge is just automatic here, because you see, when in the interaction Lagrangian, whenever there's a phi star. And what phi does, by stopping an electron or making a positron, it increases the charge by 1 unit, whereas phi star decreases the charge by 1 unit. And so you have gridlock. No change in the charge due to the action, the interaction with Lagrangian, and even if you expand this exponential even term to 57 of these LIs, still isn't going to change the charge at all. So that's one way of thinking about charge conservation in this theory. Okay, now, what is a d mu going to do? Well, a d mu on a phi, what can it be? It can be minus I p mu times an times an electron annihilation operator, or it can be I p mu, a positron creation operator. And similarly, d mu phi star, well, it's just the adjoint of that, so it's I p mu ap dagger minus I p mu ep. All right, so now, what's going to happen for these Feynman diagrams? Well, if we so now I'm going to go from left to right the way Schwartz does. Unless you want me to go up and down.
Left or right?
All right. So here we have an electron coming in, electron going out. This is P1, P2, electron, and then a photon coming in or out. This is a vertex that might be inside, would have to be inside some diagram, because you can't conserve energy momentum if you have a massive particle and a massless one like that. Okay, so what do we have? We have Ea mu, and it's phi star d mu phi minus d mu phi star phi. All right. Now, we need an A here, and we need an A dagger there. And so that means this term is going to give us an A, and it's going to give us minus I P1 mu, and we're going to have an E here. And then over here, we need an A dagger, so that means we're going to have an I P mu, but there's a minus, so it's minus I P2 mu. So the extra factor is going to look like this. In other words, it's going to be IE times minus P1 mu minus P2 mu. That's that diagram. Good. All right. Next one looks like this. But now, this is a positron, that's a positron, P1, P2. And the idea is, see, this is why Weinberg's better, because you know which way the thing is flowing, time is going. So time is going this way, and we just draw the arrow on the positron line backwards. Stuckelberg and later Feynman both both pointed out you could imagine antiparticles moving backwards in time, and that, you know, I'm sure everybody in the audience said, gee whiz, this is really marvelous, but that's not something that, it's not an idea that really led anywhere. And in fact, when you think about it, From the modern point of view, particles and antiparticles are just particles with different charge. And it just happens that you can conserve charge by having them annihilate into two photons. It's not as though antimatter is actually different from matter in any deep way. I remember I was once in a gym with on sabbatical, and we were surrounded by medical people, and one of the doctors asked me, "Is there really such a thing as an anti-electron?" So I explained.
Did you ask him if he ever got a PET scan?
Yeah, well. All right. So what do we have now? Now, once again, we have EA mu, and we have phi star du phi minus du phi star phi. Okay. Now what we need is we need a B that stops things. So that's over here, and so that's going to give minus I p mu, and then, and what is it? It's going to be p1 mu, and then we need to create the thing, the antiparticle, so we have over here, there's a minus sign here, and then we have again plus I, p2 mu, together with the E. So altogether this is IE p1 mu plus p2 mu. So these are two representative diagrams. And let me just mention once again this business of charge. Suppose Q is the charge operator. Suppose phi, well, phi is the field phi, and we have a state of charge Q. Then what we know is that this is Q plus 1 times Q plus 1 times PQ. I could just read my notes. And Q on phi star Q is Q minus 1 times P star Q. Actually, my notes were wrong. But anyway. No, they're, well, yeah, the notes are wrong. So this thing is an eigenstate of Q with eigenvalue of Q minus. Anyway, phi raises the charge, phi star lowers the charge. Okay, we've only got a minute left. Shall I just tell you what the answer is for these other ones? That one looks the same as this. Now I'm puzzled where. Ah, here we go. Okay. So this is an annihilation diagram. So E minus P1, E plus P2. So positron, electron collide, make a photon. And once again, we have this, the thing, the interaction Lagrangian times I is phi star d mu phi minus phi du phi star. And we need to annihilate the electron, and we need to annihilate the positron. And so that's going to give us IE minus P1 mu minus P2 mu. So both of the, since we're doing annihilation, both of them come in with a minus sign, and so altogether this is IE minus P1 mu plus P2 mu. And then if we have a photon turning into a positron-electron pair, P1, P2, E of plus E minus, I can't see what the time is. Anyway, this one turns out to be IE P2 mu minus P1 mu. All right, I think we can stop. These are questions first.